3-4 day 1. It's time to start solving. We've primarily evaluated, graphed, and then worked with some of the properties of exponents and logs, but we haven't really seen those properties in action from the algebra side. That's where we're going in section 4. Here's how we're going to split it up over the 2 days. What you have on the screen, 6 to the x power equals 32. That's an exponential equation, okay? That's what you're going to see today. So in the second day, we're going to solve logarithmic equations. Those are a little bit different because you would see the equation would have a log in it, okay? Today, you're not going to see that. It'll look just like what you see there, and logs will come up because, again, we've talked so much about how they're related, and we're going to start to see that today. The instructions will be relatively simple, okay? On every single problem throughout section 4 and section 5, all we're really going to do there is we're going to do the same stuff, but we're really going to focus on some of the application problems. But the instructions are going to be to solve, okay? Now, this first one's a little bit different, all right? It is something that you should always check ahead of time. E to the negative x squared equals e to the negative 3x minus 4. Okay? Kind of an interesting one. This one actually won't use logarithms at all because it's got a feature that you should always check for right away. Notice on both sides I've got an exponent that's base e. Okay, in fact, what I should do now is kind of getting ahead of ourselves a little bit, but not really. Here's the next one that we're going to do. You might be thinking, why are you writing out the next one? You haven't even done the first one. I want you to just compare them. Okay? This little shortcut that I'm going to show you, the first one you can do because it has 2 exponential expressions on each side of the equation. The next one we're going to do doesn't. Okay? 3 times 2 to the x power equals 42. What happens, and the reason we don't need logs at all, is you can simply get rid of each of those exponents that are base e. Okay, those can just cancel. If there's 1 on each side like that, they can just cancel out. And yeah, we still have some work to do to solve this, but I want you to notice that it does not involve exponents and it doesn't involve logarithms. Okay, that's something you should always check for right away because it really does simplify the process. It won't come up all that much, and in fact, you won't see it again in this lesson, but always check for that. You may have noticed here that this takes on the form of a quadratic, because that's what we were left with from the exponents. Not a terrible one to work with. It factors really nice. And the 2 solutions would be 4 and negative 1. That's happening just because the exponents had a quadratic structure to it. You're typically not going to see that happen. On the other 4 that we're going to do today, you'll see that we get 1 single solution, and that's typically going to be the norm that you should expect. That when we were finding zeros of polynomials, a lot of times a tricky part of it was you had to figure out how many zeros you'd have to find. Like a quadratic there could have 0, 1, or 2 solutions. That's really not going to be the case with exponential expressions. You should be expecting far more often than not, you're just going to get 1. All right, so here I mentioned on this next one that canceling thing isn't going to happen. So my first step would be to divide by 3, and I get to that. Now this really is the key step, okay? Because this is where a logarithm comes into play, and we haven't used them in the way that we're going to use them now. We have talked a lot about how logs and exponents are inverses. Okay, algebraically, they're opposites and they would cancel each other out. And this is where we need them. Okay, the step I need to make right here, because the tricky part is that what I'm solving for is up in the exponent, but I can take care of that. If I take the log base 2 of each side. That's really what it does for us. That's big on the left side, is the exponent and its base and the log cancel each other out, and all we're left with is x. And on the right side, we have log base 2 of 14. Okay? Now this is going to require us to go to the calculator, and the quickest, easiest way to get it from the calculator is probably to change bases, because you don't have to go and use any other features on the calculator to use log base 10. It's right on the bottom left. So that's what I would do, is just do log base 10 of 14 divided by log base 10 of 2. You'd go to the calculator and see you would get 3.807 on one like that. Rounding it to 3 decimal places is fine. Worth noting, on most of these, you're going to see that happen, that you're probably going to go to a calculator to evaluate the logarithm eventually. And as always, when we do logs in the calculator, you should expect to get some decimals. All right, let's move on to the next one here. Let's do e to the x power plus 5 equals 60. First move would be to subtract 5. Okay, and I want you to compare this to 2 to the x power equals 14, and I want you to see that these equations have a really, really similar structure to them. Okay, we have this constant over on the right side. Before it was 14, but now it's 55, but it's just a number over there. But the key is over on the left. We have a single exponential term that's base e. Okay, this is always the point where it's time to take a log of both sides. All right, now notice here, different base, different log. I'm not using log base 2. This whole problem is base e, so I'm using ln to get those to cancel. And then my solution is just simply the natural log of 55. Okay, now you're going to see it's nice when we have base e, and we use them a lot. You're going to see that. And you may notice at this point when we go to the calculator, it's nice because we don't have to use a change base, right? Base e is one of those bases that works well with our calculator. So I just type that in. You could literally just type in ln of 55, and it would be just a little bit over 4. Okay, just a little bit over 4. And down here, I want to show you one that's got a little bit more going on. Let's do 2 times 3 to the 2t minus 5 power minus 4 equals 11. Okay, a little bit tougher one, but a good one to see. Okay, basically on this, I'm going to try to throw, for the most part, everything at you that I can. Okay, like a change of base, lots of steps of solving. It's always good to have one of those in your notes where there's just a lot going on the problem. First step, and obviously if you wanted to, if you felt like those first 3 problems went well, you could certainly pause at this point. If you want to, take a shot and solve this one, feel free. You'll have a work solution whenever you hit resume. Second step would be to divide by 2, and we arrive at the step where we need to take the log of both sides. This is the 2 to the x equals 14, and then e to the x equals 55. This is the same step. There's still a little bit going on in the exponent, okay? But I can't deal with that until I take log base 3. But what tells me I need to do log base 3 is there is just one term on the left side. It's an exponential term, and it's base 3. So unlike the first two, after I do the logarithm and it cancels out, I don't just have x, or in this case t, by itself. I still have a little bit to do. And in fact, I'm looking to kind of look ahead here. I'm already going to switch this. Okay, log base 3 of 7.5 is obviously going to require us to go to the calculator. But it's going to be easiest if we do a change of base, so I'm actually going to do that right now. I wouldn't go and evaluate that until the very end, because we actually have 2 steps of solving left. When you get to this point, remember that expression on the right side is just a number. Okay, and if you actually did go right now and evaluate it on a calculator, you'd see it's like 1.83 or something like that. Okay, so I'm just going to leave it because I don't want the rounding error, but that should be treated like a number. Okay, the next thing I need to do is add 5. So I still have this log of 7.5 over log of 3. Remember, that's just a number. Plus 5. And then here, I would get close to my solution, as I have to divide both sides by 2. And this is the point I would go to my calculator. I'd start with typing in that log of 7.5 over log of 3. Then I'd add 5 to it, divide by 2. And you would get about 3.417. All right, really section 5 is primarily devoted to application questions, but, well, you know me. I love my word problems, so I'm going to work one in today. Why not? The other element this one has that I want to cover is that you have to write the equation yourself. Okay, here's what we know about this problem. That seems relevant to writing the equation. The interest rate, this is huge. Okay, we covered that earlier as to what compounded continuously means. There's 2 kind of ways we could approach interest problems. One is if it has a compounding period, okay, which we had said would be like your principal times 1 plus your rate over your compounding period to the nt power. This doesn't mention a compounding period, so I don't think that's the way to go. And then you had continuous, which was the special case of base E. And that seems to fit this, okay? With this compounded continuously, it means it's base E. Really common mistake, make sure that the rate gets switched to a decimal, otherwise you'll get some really weird answers. You would find that this investment is going to grow awfully quickly if you put 6.75 up in the exponent. Now, an equation, by its nature needs an equal sign. So what has to be over on the other side? Well, it's asking us about doubling our money. So it's how long is it going to take for this $500 deposit to grow to $1,000? Okay? That's what we need to solve. And you should notice that it, looks pretty darn similar to the ones that we were doing earlier. First step would be to divide by 500, which would give us that. Okay, and I want to point out here that as far as this solution goes, the $500 amount really wasn't all that relevant. What this is really going to tell us is if you made any investment of any size, how long is it going to take the money to double? Because if the interest is compounded continuously and you're at this rate of 6.75%, the initial investment doesn't matter. It would mathematically take the same amount of time for it to double. This is the time to do a natural log on both sides. Okay. Again, what told me to do that was on the right. I have one term. It is an exponent, and it is base E. Natural log, base E cancel each other out, and that right side just equals that. And we are actually pretty darn close. There's just one step left to get T completely by itself, and that would be to divide by 0.0675. And what I see on the left side, that's what I would have to go to my calculator and plug in. It's a base E. Again, that comes up anytime interest is compounded continuously. Those work out nice because our calculator has a base E button, and in this case it has an ln button, so that's easy to plug in. ln 2 over 0.0675, and we would see should take a little bit over 10 years for that, for that investment to double. One last thing that I do not want to work through, we're going to do this problem in day 2. I just want to give you a sneak peek in terms of what we're doing. Okay. That is a logarithmic equation. Okay, we'll talk a little bit as to how they're different and some of the differences in how they're solved. Okay, the ones we did today were all exponential because they had expressions in it that were exponents. This one doesn't, but it has this ln of t, and in day 2 we'll take a look as to how we handle that.